we looked at discrete Fourier transform last time. In simple words, discrete Fourier transform was a Fourier transform on the group Zn. Remember, this was all the numbers modulo n, and the operation was addition mod n. A simple way to describe this is by saying it's a unitary transformation where the unitary matrix is given like this. It has n rows and n columns. Let me index it from 0 to n minus 1, and the jkth entry is omega to the jk, where omega is the nth root of unity. I can also call it to the power 2 pi I by n. So I should say that it is the primitive root of unity. This gives you the meaning of discrete Fourier transform. It will take a vector in c to the power n and give you y element of c to the power n, where y is fn multiplied by x. This is the usual matrix multiplication. This is what we called discrete Fourier transform. What is QFT? We also described QFT. We will just say, suppose x and y are normalized. This means I can assume that x and y are quantum states. In that case, I want QFT to take the state x and give me fnx, which I can call y. If you are confused, I am calling this vector as x and this vector as y. The thing to notice here is that this is the output. This is a state with amplitudes as Fourier coefficients. So we do not get exactly what we want. One more time, QFT does not imply DFT. It is something similar. It gives you the final state where the amplitudes of the state encode your Fourier coefficients, but it does not give you the Fourier coefficients directly. It's not the same problem, it's a related problem. But let's see, we can do it really fast on a quantum computer. How can we do it fast on a quantum computer? That's what we want to see. Another simplification, we will assume that n is equal to 2 to the power k. It's a power of 2. For other n's, the process is slightly different. You can refer to Andrew Child's course notes. They are given in course notes also. That's where you can look for the modified procedure to do the Fourier transform when n is not a power of 2. But from now on, let's assume that n is a power of 2. Why did we assume n is equal to the power k? Because this will allow us, this will permit us to write the Fourier transform as a product. What do I mean by it? Let's do the calculations. I have to apply this matrix on some state j. Remember, j is from 0 to 2 to the power k minus 1. I can view it as a string 0, 1 to the k. This is something which I have done multiple times. So I can say that I want to apply it on j1 to jk, which is same as this. It's just a renaming. And then by the formula of Fourier transform, This will give me this state. The amplitude of state L would be omega JL. This is coming from the basic definition. You can see it from the matrix here. Nothing changes here. But now, if you look at L, even L is a binary string of length to the length k. Let me say that L has a binary representation of L1 to Lk. In that case, the state becomes this, and now I want to write it in terms of L 1 to Lk. That is just the transformation, and you can do it easily. And now the state itself. Okay. This is the final state, and the amplitude is the binary representation of number L. Now the product property will be in use. This summation can be distributed because summation in the exponent is like multiplication. So we can give the corresponding amplitude to the state itself. And now there is a product of these states, or since these are states, I should actually say tensor product, where LH will have an amplitude omega j to the power k minus h LH. You can take some time and make sure that you see this transformation. This is just distributing the sum to the corresponding state. Once I have done this, I can simplify. I know that omega is, e to the power 2 pi I by n, which is equal to e to the 2 pi I to the power minus k. As soon as you substitute it here, cancellations will happen. Let me write the new state. This will become, with the normalization factor, all summations, I should say Lk, not Lh, but the state Lh, its amplitude will be simplified and it will be 2 pi I j Lh to the power minus h. This is my state. I'm doing calculations. I'm not changing my state. I'm just saying what the state looks like. Keeping n is equal to the power k allows me to write my state like this. And now I can put these summations inside. Notice that phase will be applied when LH is 1, otherwise that means when LH is 0, no phase. Distributing the sum, I will get that my state is product over, I should say H is equal to 1 to k, and then 0 plus the corresponding phase on 1. This is what I meant by writing state as a product, or writing my output as a This gives a simple transformation. It tells me that my state J1 to Jk, if I want to write it, I have a normalization factor which I will not worry about. But after that, the first state goes to 0 plus e to the, now if I take h is equal to 1, it is going to 2 pi I j multiplied by half. Notice that j is some j1 to jk in binary. So j by 2 is j1 to jk minus 1 dot jk. This should not confuse you. This is just the binary representation as it is. The dot shifts 1 point because I'm dividing by half. In the normal representation, when I divide by 10, your dot shifts one place. Now I'm dividing by half. It's a binary representation, so dot will shift one way. Since e to the 2 pi I is equal to 1, any integer part I can ignore, and I will only get 2 pi I 0 point jk, the final thing. This is the first state. Similarly, I can write other states. 0. Now in the case when h is 2, I am dividing by 4. That means I have to shift the dot twice. It is 2 pi I 0 point jk minus 1 jk and 1. Again, the part before jk minus 1, this will be an integer, and that could be taken off because e to the 2 pi I is equal to 1. Doing this continuously, the final state would be this. This gives you an easy representation of the state, and now we want to see how to do this. We can do it one by one. Let us look at the first part. How can we create state 0 plus e to the 2 pi I 0 point jk 1? If you think about it, it's not really hard. If jk is equal to 0, then this is a plus state. If jk is equal to 1, then this is a minus state. This is saying I take the state jk and apply Hadamard on it. The state will become 0 plus e to the 2 pi I 0 point jk 1. Very nice. What else? We also need to convert jk minus 1 to this state. Again, I can think of this phase in two parts. This is e to the 2 pi I jk minus 1 divided by 2 multiplied by e to the 2 pi I jk divided by 4. These two phases has to be applied. The first part is just a Hadamard operator like before on jk minus 1. What about the second part? Remember, we had talked about phase operators and their square roots. This is like that. These are things which we have studied before, and since we have access to all 1 qubit gates, we can assume that these gates are also there. We can even apply controlled versions of it. So to get these phases, I will take my state jk minus 1. I will apply Hadamard. That will give me this part, and then I will apply an R2 with control on jk. This will give me the final state. It will be instructive to go through these operations yourself and convince yourself that this is the final output. You can keep doing this one by one. Let us see a circuit for QFT on these many qubits. I mean 3 qubits, but n is equal to 2 to the power 3. How will I do it? I will have 3 qubits, J3, J2, J1, and first let me transform J1. I will apply Hadamard, then I will apply R2. This will be using J2, and then I will apply R3. This will make sure that J1 is in the right place. For J2, I will apply Hadamard, then apply R2, but this has to be controlled by J1. And then I will apply Hadamard. Notice that I want the reverse of it. This should be my first qubit. This was my third qubit, but this I want to be my first qubit. So the order here is reversed. The final operation is a swap operation. You might ask, how do we swap? But you have seen swapping using C0 before. It's a good idea to remind yourself how to do swap using C0. But assuming swap, you can make a circuit now for any QFT on 2 to the power k things. You will transform them one by one. Remember, we will apply this form. This goes to product, probably I should say 1 by root 2 h is equal to 1 to k, 1 by root 2, and then the phase here will be e to the 2 pi I j multiplied by 2 to the minus h. And each of these states we can obtain in this manner. This will allow us to perform QFT. We have seen a circuit for QFT for k is equal to 3. You can generalize it and end with a swap operation. That shows how to do QFT on